Hi, my name is Carlo Giacometti, and today I will be talking about the new functionality around audio processing in version 12 of the Wolfram language. So audio was introduced as the first-class citizen in the Wolfram language in version 11. In all the evolution between version 11 and version 12, we added a lot of support for generating, capturing, and searching for audio signals. We have added and improved capabilities to do audio processing and audio analysis, and we have introduced very high-level audio analysis functions that rely on a machine learning or a neural networks backend, like audio identification, speech recognition, pitch recognition, and much more. The other thing that we added was a very tight integration with all of the machine learning and neural net capabilities of the language. And there is a very, very powerful interplay between audio and these domains of the language. So I'm showing here the page that tries to summarize the main features introduced in 12 for audio processing. You can see it does have a bunch of examples. What I will do is I have a notebook with a minimized version of all of these examples, so I can show it to you in an actual notebook, not in a web page. So let's move there. So the first group of examples is about audio sources. So sure, we have audio processing capabilities, we have audio analysis capabilities, but you still need different ways to gather these recordings that you want to process or analyze. So one of the things that was introduced between version 11 and 12 was the capability of recording from a microphone. And we do this with the function audio capture that creates a very nice GUI, and as you can see, records directly from my microphone. So let's do that. Hello, this is a test recording. And we get exactly what was recorded. Hello, this is a test recording. So we can now use all of the analysis functions. For example, let's compute a spectrogram. Here we go. We could attempt to recognizing what words were spoken into this recording. Let's see if that is true, or if my machine, well, it definitely did not understand what recording was, but I guess it was a fair attempt. And we introduced a function that tries to identify what kind of signal you're looking at. So this is one way of recording from a microphone. Another set of functionality that still allows you to record from microphones is the whole programmatic playback audio stream framework. In that case, there is another function that is just called audio record that has pretty much the same structure. If I say audio record, hello, and then I want to stop the recording, and this gives me something that comes out of what I just recorded. I can visualize it with little effort. Here we go. So the internet is another big source for random recordings. And we have introduced a new function that's called web audio search that searches for audio signals on the Freesound website. So as you can see, I will not evaluate this. My connection is being iffy at the moment. I get a collection of recording as results in a nice data set with meta information, and you can download you can use criteria to select filtering with this meta information. So for example, here I want signals with a duration between 5 and 10 seconds. And of course, all of these are then, the sample of these is then downloadable, and you can do your analysis and processing however you want. The last source of audio signals that I want to show is speech synthesis. It works pretty much as you would expect. You give it a string, and a signal is returned.
Once upon a midnight dreary.
And again, we can easily plot it, plot the spectrogram, which gives us this nice time frequency representation, which is, I feel, the nicest to understand the contents of an audio signal. And we do have some freedom in the synthesis. For example, we can choose a different voice style. In this case, the synthesis will happen using this specific voice.
Once upon a midnight dreary.
Clearly, this voice is not optimized for English. It is something that probably belongs to another language. To visualize what kind of voices we have available, there is also a very convenient function that holds all of the meta information that is necessary. For example, if we look at that voice that was just randomly chosen, we can see that it is a voice optimized for Polish. So we can look at what the languages are and plot a very nice word cloud, hopefully. As you can see, this depends on what voices you might have on your computer. So, for example, on my computer, most of the voices are in English, but they cover still a huge amount of different languages. So I mentioned before about the programmatic playback framework and audio record to record audio. Of course, that is not the only application. As programmatic playback hints, this is definitely very useful for playback. So it gives you a different way of playing an audio object in a programmatic way without having to rely on a GUI. So for example, here I defined this audio object, but if I just say audio play of that audio object, that will play as well, without me having to interact with any graphical user interface. So, what I'm doing here is I want to analyze the snippet of audio that is currently playing, not the whole signal. So I create a stream out of the audio object. And I can plot the audio. As you can see, there's a simple sequence of notes on a piano. And here I am using the current audio property of the stream. So when the stream is playing, querying, for example, let me demonstrate here. I can query the current audio property. This will give me a short snippet. You can see that the duration is, let's look at the duration of this, is about 0.18 seconds. This is the length of one buffer in the playback. So I have access to the currently playing buffer of the stream. So this function simply takes that current buffer and plots it with some nice inset. And again, here, what I will do is display the basic waveform and then a magnified version of the buffer. Let's see how that looks. And you can see that the inset is actually aligned with what is currently playing. With the same kind of thing, we can do exactly the same thing on exactly the same signal. Now, though, let's look at the spectrum rather than the waveform. And what we want to do is, instead of just visualizing the current buffer, we can do some real-time analysis of the signal that is playing. And in that fashion, I can apply the pitch recognize function, which we will look at later, that finds the main pitch of a signal and plot that on top of the spectrogram. So let's look at that. You can see how the fundamental frequency is tracked and computed in real time. This is not an offline analysis. This is, as the stream is playing, the analysis is performed buffer by buffer. So yeah, these are the functionalities for getting audio signals and playing audio signals. Now, what are the high-level functionalities that we introduced into versions up to 12? So one that I quickly showed before is audio identify. Audio identify tries to figure out what the contents of a signal are. So here we have the drum recording. And audio identify, in this case, does a pretty good job. It is possible to restrict the identification to a specific category. So this is essentially equivalent to asking to the language, what are the contents of the recording in this audio object, assuming that they are made by tools. As you can see, the result is weird because just this constraint is weird. But this allows you, for example, to restrict identifications to animals or to the correct category that you already know is contained in the signal. And we can compute the probability of all of the results. One cool application is, for example, I can create a signal that has 3 different components. First a bird, then drums, then a cat sound. If I try to identify the whole signal, you can see that the drum sound is definitely the prominent one. But what I can do is chunk up this long signal into 1 second overlapping blocks and identify each of those. And you can see I am using audio block map there, which takes the signal partitions and applies a function to each partition. And you can see you get a bird sounded identification, a bass drum identification, and a cat sound identification. And you can easily plot these results. And this fits with how we constructed the signal. Again, another function that was introduced in version 12 is speech recognize, which uses a neural network backend as audio identify. That does pretty much, what you expect it to do from the name. So this is our signal. That's validated.
Good job, I guess. Good job, I guess.
Etc., etc. As usual, we can look at the spectrogram just to have an idea of what the evolution of the signal is. The speech recognition happens in 2 steps. There is first an acoustic model that gets a very raw output that might have a lot of spelling mistakes. And then a language model is applied to the result to correct the possible spelling mistakes. You have seen before, it is not always correct, but as you can see, you get a nice progress indicator that is telling you now the acoustic model is running. Let's see how long it takes. My machine is not happy with. And of course, the one thing that I want to point out is I am running this on my machine while sharing my screen. So that's not great. But if you have a newer machine, or if you have a machine with a GPU, all of this will be essentially instantaneous. Another function with the neural network backend is pitch recognize. Pitch recognize tries to figure out the pitch of monophonic sounds, so sounds where only one note is played at a time. So we can start with this recording or excerpt from a Bach fugue. And we can use pitch recognize. There are, I guess, 2 main ways to use it. One is just calling the function, plain and simple. and the other one is to use the creep method, which is based on a trained neural network. And we can look at the differences between these two results. Again, this neural network method will again greatly benefit from having a GPU, which my machine doesn't. And as you can see, the second result, the GPU one, it is cleaner. It is cleaner at the cost, I guess, of a bit more computational effort. So what we can do actually is pitch recognize does have an additional argument, a second argument that selects what kind of output you want. The basic one is just a time series with the recognized frequency in hertz as values. But for example, if I ask for sound note pitch, the output will be a sequence of integers that are compatible with what the input of sound note is. So it will actually recognize the note, the correct pitch, and it will transform it into a sound note specification. So we can define this simple function that essentially grabs that recognition and generates a sequence of sound notes. So what I'm doing here is taking a recording and then transforming it into a score that has the same sequence of notes. Unfortunately, if I play the sound object, you will not hear it just because of how audio sharing works. But I can easily convert it to an audio object again, and you will be able. And since pitch recognize computes symbolic information, we can resynthesize that with a completely different sound. For example, a violin. And again, I will have to do the trick using the audio object so that you will be able to. Okay, so these are the three neural net-based functions that we introduced in version 12. One cool thing, I want to show just one quick cool application that you can do with all of these audio functionality when it is integrated in the rest of the language. So one example is how to build a question answering machine. We have a simple recording of a spoken query. Who wrote The Art of Computer Programming? So we can speech recognize it. Again, my machine might make this step a bit slow. Then we can send the query to Wolfram Alpha. And we can again query Wolfram Alpha to generate a string that then we will be able to speak using speech synthesize.
The book The Art of Computer Programming books was written by Donald E. Knuth.
So we have a pipeline where we start from an audio object and we end with an audio object, going through speech recognition and querying a knowledge engine. So I think that is pretty cool, and especially the fact that it took very few lines of code to do that. One other area that we introduced in version 12 is analysis and manipulation using the short-time Fourier transform. For those of you that might not know this, the short-time Fourier transform is essentially the basis of the spectrogram. You partition a signal into overlapping windows and then do a Fourier transform on each of the partition. So you get a sequence of vectors, which forms, I guess, a matrix or an image, depending on how you want to look at it. And one axis is the time, and the other axis is the frequency. So this gives you a very nice time frequency visualization or representation of your signal. So let's start with an example. This is
one small step for man,
a very noisy recording. So I can compute a short-time Fourier transform. This is a new in12 function. And this outputs a standalone object that holds all of the information that is in the original audio object, but it is computed, the short-time Fourier transform is computed. So you get time and frequency information. You can see here all of the various parameters, dimension, sample rate, data type, whatever parameters were used for computing. You can visualize this information using Spectral. Again, time and frequency information. And this is you can almost invert exactly this operation. In this case, we use the inverse short-time Fourier transform. And we can invert it because all of the information, the redundant one and the phase information, is maintained in this representation.
That's one small step for...
If you just computed the spectrum, the phase information would be discarded, so the inversion would not be perfect. So what can you do with this? Well, you can manipulate, you can transform a signal into its time frequency representation, do some manipulation, and then transform it back. So for example, one silly application is for example, vocoding. The idea is that you have a signal that you call a carrier and another signal that is called a modulator. And you want to impose the spectral envelope of the modulator onto the carrier. So the pitch of the carrier is preserved, but all of the articulation and the timbre and the formants, etc., are determined by the modulator. In this case, we will have a modulator that's a voice signal.
We are the robots.
And the carrier, instead, is just a bunch of harmonic sounds. So you make sure they are the same length. And just by, so for example, here I am computing the short-time Fourier transform of the modulator. And what I do here is apply mean filter to just extract the spectral envelope, not a whole short-time Fourier transform. And by modifying the short-time Fourier transform of the carrier just by a multiplication, I get the short-time Fourier transform of a transform signal. So I bring it back using inverse short-time Fourier transform.
We are the robots.
So you can see the harmonic content is the same as the carrier, so the various notes, but the speech signal is still kind of intelligible. So we have some functions that do some kind of modifications in the spectral domain automatically. For example, audio spectral map. In this case, I want to decrease the noise of some spectral components. So I define a nonlinear function that then gets applied to each of the time frequency bins of our signal. And this is now significantly less noisy. I was saying before how if you discard the phase information, you cannot really reconstruct your original signal exactly. But we did introduce an inverse spectral function, which instead computes an approximate inversion of the signal. So this is an input image. What will happen here is we interpret this image as a spectrogram of a recording. And so what we want to do is guess what the phase is. There are several algorithms that can be chosen as a backend. The main one is an iterative algorithm that is called Griffin limb. So we guess the phase, and then you do the inverse short-time Fourier transformation. So we can do that pretty easily. And this is the sound that results from this image as a spectrogram. And we can kind of verify that by computing the spectrogram of the calculated signal. I mean, same thing. We can use a different image as an input. This is so black and white images work very well. The black will be silenced. The white will be loud sounds in that time frequency region. So here is this, and then this goes down, and this bubbling is the shoulder, which is pretty funny. Anyways, and you can again look at the spectrogram and check that we actually did the proper transformation, and you can kind of reconstruct a similar kind of information. So the last bit that I want to talk about was improvements and new things in audio analysis. So audio local measurements was introduced in version 11. There have been big improvements, especially performance-wise. But yeah, for those of you that have not used it, this is a speech signal. Audio local measurements allows you to compute properties that are obtained by partitioning the signal into overlapping windows and then applying whatever measurement to each of those partitions. So the output is a time series. So you get an idea of the evolution of some properties of the signals over time. In this case, audio local measurements is computing the formants, which are some of the resonant frequencies, I guess, in the a speech signal. And yeah, they are visualized on top of a spectrogram. You can compute several properties at the same time. In this case, you can see I get 3 results of measurements in just with one call. This is done efficiently. Again, we are visualizing those on top of a spectrogram. If you want more control of what happens on those partitions, you can use audio block map. Again, same kind of idea. You partition your signal on overlapping windows and apply a function on each of the windows. The difference here is that we can control what this function is. So for example, here I define a function that computes the loudness. The partition here is just a list of numbers. So I take the square of it, the mean, and then the square root, and then I transform that into decibels. And I define another color that takes a numeric input and then outputs a color that will be a blend of green, yellow, and red according to that value. And here you can see that with audio block map, I will apply a function that will compute the loudness and will return a color according to the loudness value. And we can easily look at what one of these outputs are. Is, as you can see, just a list of colors that are related to how loud that signal is on that partition. And we can have a nice visualization as a bar. And we have collected here all of the data that is in our example data collection. So we can have a global visualization on how the loudness of each of these signals evolves with time, where red is very loud and green is very quiet. Another thing that was added between version 11 and 12 was functionalities to allow you to compute distances between audio signals. So here we are gathering recordings of various kinds of instruments. And it is pretty easy to compute the distance between 2 different recordings. The distance function is up to the user. For example, here I am using a preset that computes the distance between a frequency representation of the 2 signals, in this case, just the Fourier transform. Well, I guess the spectrum rather than the spectrogram. And it is possible to compute a distance matrix between a collection of recordings. In this case, I am specifying that I want the distance computed onto semantic audio features, something that where the extractor is aware of what an audio signal is and knows characteristics about it. And we can then plot and see what signals are more similar to each other. So one thing that was also added in version 12 is a very experimental framework for annotations. So all of these analysis that you can do is, of course, I mean, the crucial part, very important. But there is also a question, how do you store that? Because many times you don't want to, for your analysis or your annotations, because you might want to just have, I don't know, a tagged recording of speech where the tags say which word is spoken where. This is not something that you have computed, but it's something that you have imputed manually. So how do you store all of this information? One crucial thing, in our opinion, is that you should be able to store information linked intrinsically with the audio object that you're analyzing. So for example, here we have a simple signal. There's nothing special about it. But say that now I am building a data set to train a neural network, or just to do some kind of analysis, meta-analysis on a collection of signals. I want to store, for example, annotation about events that happen at specific times. So in this case, I can use audio annotate, and you can see I group this annotation under a label, and I give it a list of events. You can see there is a time and a value. Each of these annotation is a time and a value. So this will tell me that at time 5, this value, and there is no restriction of what the value is. As you can see, I have colors here, a string, etc., etc. And you can use audio annotation lookup to retrieve the annotation and inspect them. And these, as I said, are stored inside the audio object right now. You can also use audio annotate to compute automatically annotations. And all of these are based on pre-existing functionality that is in audio local measurements and audio intervals. So here, I want to annotate the moments in the signal that are loud. And then, again, I am visualizing the result using audio annotation lookup. And you can see I get a bunch of intervals that tell me where the signal is loud. Tells me what time the loud signal, the loud subsegment began, and how long it was. And we have, again, this framework is very experimental, but you can use audio plot to visualize the annotations along with the waveform. And you can see these are the areas that we think are louder than others. And as you can see, oops, let me magnify this properly. As you can see, they correspond to the actual onsets of the drum hits. One very important thing that hopefully you will never notice, but is crucial to all this, is all of these functions that compute things onto partitions of audio objects have gotten a massive, massive speed improvement on version 12. For example, here, audio local measurements, the total property, you can see that the average speed up is 5 times, which is pretty impressive. For spectral properties in audio local measurements, this specific one, the average speed up is 26 times. So yes, you get massive speed gains that are pretty much independent on the file size. Audio block map, again, also big speed up. Spectrogram array also leveraged the internal framework that we built. So this also has a massive improvement for audio objects. And something that you might not expect, or you might not pay too much attention to, but is also super important. Because, I mean, all of these properties, all of these functions that apply to partitions, in the end, use window functions to smooth the edges of these partitions. We have a massive improvement in the speed of computations of all window functions. And the average speed up here is a ridiculous 10 to the third, which is, yeah, pretty ridiculous. So yeah, not only new high-level functionality, not only improved measurements, but massive performance speedups. And I think this is all that I wanted to share with you guys. If you want a bit more details, you feel free to go to the new in audio processing product page, and feel free to explore all of the pages. As I said, I did keep most of the example in the notebook I just showed you, but there is definitely more content here, and there definitely is more content in the documentation. One thing that I want to point out is that this is not all of the audio, all of the new audio stuff that we want to present. Something that I assume will be presented in the future is the machine learning for audio page that will showcase all of the connections between the audio framework that I just talked about and the neural nets and the machine learning framework. And this allows for very, very powerful applications as well. Again, that is all. Thank you very much